Welcome to another Ask Me Anything event. If you're watching this on YouTube, I invite you to join me live next time. We have these every Saturday at 11 a.m. Eastern, and you can join for free by starting your free trial on quantreasoning.com. Couple of rules that we were all forced to memorize in elementary school. And they looked kind of something like this. Even plus or minus even always equals even. And, even plus or minus odd always equals odd. And odd plus or minus odd always equals even. We were forced to memorize these rules, but hidden behind these rules is a deep understanding of remainders. So I want to kind of start from here and then work our way to official GMAT questions that are testing that understanding. When we say even, what do we mean? What is an even number? What's the definition of an even number? It's a number which, divided by 2, get a remainder of 0. So it's a multiple of 2 with a remainder of 0. And then an odd number would be a multiple of 2 with a remainder of 1. So this is just my notation for divisibility and remainders. So an even is a multiple of 2 with a remainder of 0, and an odd is a multiple of 2 with a remainder of 1. Let's just visualize the following. Have you ever seen toddlers at daycare go for a walk? It's really cute. They kind of pair up and they hold hands together. So you see these like really small children on the street going for a walk following a teacher, and they're in pairs and they're holding hands. If it works out, if they are all in pairs and there's no remainder, then you know that the number of toddlers is a multiple of 2, because the remainder is 0. If there's one child holding the teacher's hand, because there's an odd number of children, well then you know that it's a multiple of 2 with a remainder 1. That's what odd means. We can use that visualization to understand these rules on the left. Why is it that if you add 2 even numbers, you still have an even number? Imagine 2 daycare classes, each of which has an even number of children, so they're holding hands in pairs and everything works out perfectly. If you were to combine those 2 daycare classes, would you still have an even number of children? Would you still be able to pair them up such that they're holding hands and there's no remainder? Of course, you just keep them in their pairs. Conversely, if you had one class with an even number of kids and one class with an odd number of kids, and you combine those classes, it'll still be odd because the kids who are in pairs are still in pairs, and the one child that was a remainder is still a remainder. And finally, if you have 2 classes, each of which has an odd number of children, and you combine them, well, then you can take the one single child from class 1, the one single child from class 2, and have them holding hands, and now you have an even number. So that's kind of the reasoning behind these rules, and it always made me kind of laugh that we're memorizing them. There's no need to memorize these. They make sense if you visualize those daycare children. But what about other divisibility scenarios? What if we're not talking about divisibility by 2? I mean, all this pink stuff, that's just the world of divisibility by 2. What if we talk about the world of divisibility by 17, just as an example? If I say that a multiple of 17 with remainder 0 plus or minus a multiple of 17 with remainder 0 always is going to equal a multiple of 17 with remainder 0. What do you think about that? Is that a good rule? Is that always going to be true? Yeah, imagine summer camp where the children are told to arrange themselves in groups of 17 for some kind of activity. So group A does so, and there's no remainder. Just so happens there were a multiple of 17. Group B also arranges itself in groups of 17, and there's no remainder, and works out perfectly. If you were to combine group A and group B, you'll just tell the kids to stay in their groups of 17. Why would there be? The remainder wouldn't just show up from nowhere. So I feel like this rule that we just created, that we just invented here in the bottom, is exactly the same rule as that first one, where even plus or minus even equals even. Right? In that first rule, we said a multiple of 2 with the remainder 0 plus or minus a multiple of 2 with the remainder 0 always equals a multiple of 2 with the remainder 0. So that's true for any divisor, like 17, for example. So what about if we say, I want to try to mimic that third rule, the odd plus or minus odd equals even. So let's see if we can do that. What if I say a non-multiple of 17 plus or minus a non-multiple of 17 always equals a multiple of 17? That would mimic that, odd plus or minus odd always equals even. Does this also work? What do you think about this rule here at the top?
Well, it depends on the remainder.
Precisely. So why is it that here it doesn't depend on the remainder? Why is it that here the rule does work? And let's write this rule the way that I think we should write it, which is multiple of 2 remainder 1 plus multiple of 2 remainder 1 always equals multiple of 2 remainder 0. Why is it that this rule does work, but the one at the top does not?
Because in the second one, you have one child left over from each group, and you can pair those two children together to make a pair. But above, you don't know the number of children that you have left per group. So you could have 15 left in one and 10 left in the other.
That's right. I think what you really what it gets down to is when we say non-multiple of 2, we know what the remainder is. There's only one option. In fact, maybe that's why we invented a word for it, where we call it odd. You've got even and you've got odd. I think it's because there's only one kind of non-multiple of 2. You were just one above or one below, if you prefer to think of it that way. You're like just slightly off being a multiple of 2. You're just one away. Whereas with divisibility by 17, there's a lot of different types of non-multiple of 17. Right? Are you 1 above a multiple of 17? Are you 2 above? Are you 3 above? All the way up to 16 above. There's 16 different types of non-multiple of 17, and if I don't know which kind of non-multiple of 17 it is, then I can't say anything about their sum or their difference in terms of the remainder. So let's take this one step further, and let's see if we can make some interesting inferences here. If I say that a multiple of 17 remainder 3 plus a multiple of 17 remainder 9, let's say, okay? Can you tell me what remainder in the world of divisibility by 17, what remainder that sum would have? Visualizing summer camp again, if group A split themselves in groups of 17 and there were 3 kids left over, and group B split themselves into groups of 17 and there were 9 kids left over, and now you're combining groups A and B together and asking them to put themselves in groups of 17, you'll just have those 3 leftover kids from group A and 9 leftover kids from group B, put them all together, well, now it's 12 leftover kids. I still can't make a group of 17 from those 12 extra kids, so the remainder is 12. That's correct. Multiple of 10, remainder 5, plus multiple of 10, remainder 2, will give you a multiple of 10 with what remainder? Is this at all easier, or do you feel like divisibility by 10 is easier to think about than divisibility by 17? You don't see a difference. All right, you might, though, with this next question. Multiple of 10, remainder 8, plus multiple of 10, remainder 5, equals multiple of 10 with what remainder? Do you think that it would be harder with divisibility by 17? So this is 3, you're right. Why is it harder with multiple of 17, let's say remainder 12, plus multiple of 17, remainder 13? Why is this harder? Or why was the one with the divisibility by 10 easier? I think the difference is that our number system is base 10. Our number system is not base 17. So we've been doing addition for years and years and years. And if you remember when you first learned addition, you had to kind of memorize, well, if my units digit is 3 and my other units digit is 9, and I add them together, I'll end up with a units digit of 2. And then you carry the 1. Remember carrying the 1 from first grade or second grade? So we have a lot of experience doing this with divisibility by 10 just because our number system is base 10. But there's an interesting takeaway here, which is if you know the remainder in the world of divisibility by 10, then you know the units digit. In fact, that's just another word for units digit. The units digit of a number is the remainder when you divide that number by 10. And that's something that I've seen tested in the GMAT a fair bit. So keep that in mind. If you know the remainder when you divide a number by 10, well, then you know that number's units digit. It's the same thing. In this case, what would be the remainder in the world of divisibility by 17? That's right. Again, visualizing that summer camp, if I had 12 kids left over from one group and I had 13 kids left over from the other group, adding them all together, I get 25. But hey, I can make a group of 17 from those 25 kids. So I will. And then how many will still be left over? 8. So the remainder is 8. That's exactly right. What about subtraction? Let's try one with subtraction. Multiple of 17, remainder 3, minus multiple of 17, remainder 8, will give me a multiple of 17 with what remainder? I heard someone say a remainder of -5, but a remainder of -5 would translate into a remainder of 12 in the world of divisibility by 17. Like if we're building groups of 17 and we're missing 5 kids, it's like, oh, if we only had 5 more kids, we'd have a group of 17. Well, what does that tell us? It means that we have a remainder of 12 because that's 5 below 17. We're missing 5, so we have a remainder of 12. That's exactly right. And this is all going to come into play in the official GMAT questions that we're about to look at. All right, so this is an actual GMAT question. And as you try to solve this, I encourage you to think about or even draw a number line to evaluate these statements. So we want to know whether or not n is divisible by 7. And all we know from the free info is that k and n are integers, so not much. I'm curious, which statement would you all start with? Statement 2? Why?
There's nothing about n.
Perfect. That's right. So I also would start with statement 2 because statement 2 doesn't have any chance of being sufficient on its own. With statement 2 on its own, we know absolutely nothing about n, and the question is about n. So it's a really good idea to start with statement 2. You can go ahead and eliminate the answer choices that claim that it's sufficient on its own. So B, D are gone. What can we infer from statement 1? What can we tell from statement 1 on its own about the divisibility of n in the world of divisibility by 7? That's what the question is about. 7. In the world of divisibility by 7, what can we tell about n from statement 1 on its own? For statement 1 on its own, look, all I can say is that 2k is even, because they told me that k is an integer. So I do know that 2k is even, and I can say that n is 3 units to the right of that even number. But I can't make inferences about the world of divisibility by 7 from knowledge about the world of divisibility by 2, because those two worlds are separate. I mean, if I told you that some number is even, would you be able to tell me its remainder when divided by 7? What about the other way around? If I told you some number is a multiple of 7, would you know its remainder when dividing by 2? No, it's like a 50-50 chance. Could be either odd or even. So there's really nothing connecting those two worlds. So if all I can infer from statement 1 is about the divisibility of n in the world of divisibility by 2, then I can't infer anything about the world of divisibility by 7. And we could infer that n is odd. Maybe some of you did that. From statement 1, we can infer that n is odd, but that doesn't help me at all in the world of divisibility by 7. They're just unrelated worlds. So let's go ahead and eliminate A. And now we're going to combine the statements. Did anyone try to plot these on a number line? So with number line reasoning, we can notice that the thing that they're asking about, n, is exactly 7 units to the right of the thing that statement 2 is talking about, which is 2k minus 4. 2k minus 4 is exactly 7 units to the left of n. And so if we know the situation in the world of divisibility by 7 of 2k minus 4, we can infer the remainder when dividing n by 7, because we know exactly how far apart those guys are on the number line. So I don't even need to go ahead and say, yes, n is divisible by 7, although we do know now that it is. I could just say, hey, I can infer whether n is or is not divisible. Like, I can infer the remainder when dividing n by 7. From combining the statements, I can infer the remainder when dividing n by 7, and therefore it's sufficient, and we can go ahead and pick C. Whenever you're practicing at home, really try to avoid testing cases, because it's a crutch. I know that a lot of people and even a lot of test prep companies really emphasize testing cases. And I think it's a mistake, because it's like, it really is like a crutch. You don't show up at the Olympics for a running race with your crutches. You leave your crutches at home. Or maybe I should call them training wheels. You don't go to the Tour de France with your training wheels on your bicycle. We need to move on from testing cases if we want to really do well in this test. Let's try this one. So just in terms of rephrasing this question, when I ask myself under what circumstances would n be divisible by 6, it would have to be divisible by 2 and it would have to be divisible by 3. So to answer this question, I would need to know whether the remainder in the world of divisibility by 2 is 0, and also whether the remainder in the world of divisibility by 3 is 0. Although we should be careful here, it's a yes-no question. So if I know that the remainder in one of those worlds is not 0, I'm done. If, for example, if a statement told us in the world of divisibility by 3, the remainder is 2. Well, then I don't care about the world of divisibility by 2 anymore because I already know it won't be a multiple of 6. And that's kind of interesting. If I find that the remainder is 0 in one of those worlds, then I also need to find out what's the remainder in the other world in order to answer the question. But if in one of them the remainder is not 0, I'm done. In order to be divisible by 6, you have to be divisible by 3 and you have to be divisible by 2. So if you're not divisible by one of those, then you're not divisible by 6. So that's the first thought that comes to my mind as I try to rephrase this question and understand what it's really asking about. But then there's also some free info. So let's focus on the free info now, because we know the free info is the most important thing on the computer screen. How does this help us start answering the question? We had a Ask Me Anything event maybe 2 months ago, where we looked at a question that had the product of 3 consecutive integers. And we figured out that that would have to be a multiple of 3 because one of them would be a remainder 0, one of them would be a remainder 1, one of them would be a remainder 2 in the world of divisibility by 3. And we might not know which one is which, but for sure their product is a multiple of 3. And that's kind of the reasoning that Theo used here for k times k plus 7. We know that k and k plus 7 are different types of numbers in the world of divisibility by 2, because there are only 2 types of numbers in the world of divisibility by 2. Either your remainder is 0 or your remainder is 1. And as Theo said, we don't know which is which. I don't know if k has a remainder of 0 and k plus 7 has a remainder of 1 or vice versa. But what I do know is that they're different. They have different remainders in the world of divisibility by 2. And since those are the only 2 options, well, then one of them has to be remainder 0. And therefore their product is the remainder 0, and therefore n has a remainder of 0 in the world of divisibility by 2. So this free info has already answered half of our question. Remember, our question was, is the remainder 0 in both worlds of divisibility, world of 2 and world of 3? This already answers in the world of divisibility by 2, the remainder is 0. Which means we have to now also find what is the remainder in the world of divisibility by 3 in order to answer this question. So what I'm thinking is, let's go ahead and rephrase the question. So having used the free info, we're really just asking, is the remainder 0? Is the remainder of n over 3 0? That's really what the question is asking. Because if the answer to that is yes, then the answer to the original question is yes. If the answer to that is no, then the answer to the original question is no. So we just want to know, is the remainder 0? Which statement do you want to start with? I agree. The first statement only talks about the world of divisibility by 2, and we already have everything we need about the world of divisibility by 2. So we can eliminate A and D, but you know what? We can also eliminate C, because statement 1 has no value add on top of what we had from the free info. So think about what answer choice C says. Answer choice C, I'm going to paraphrase it a bit. Answer choice C says that although statement 2 alone is not sufficient, when you add statement 1 to it, it is. I paraphrased answer choice C. But if statement 1 doesn't add any value beyond what we already knew from the free info, then answer choice C doesn't make any sense. Why, like if 2 is not sufficient on its own, why would adding statement 1 to it be helpful when we can see that 1 doesn't offer anything new that we didn't already know? So we can eliminate A, C, D. When you all look at statement 2, do you think there's any work that we have to do there, or can we just see that it's sufficient on its own? I think with a bit more experience on number lines, you wouldn't need to. And here's why I say that. If I know the remainder when k is divided by 3, so multiple of 3, remainder 2. That's what we know about k from statement 2. If you know that, you could draw a number line and infer the remainder when k plus 7 is divided by 3. And after you've done that a few times, you won't even need to do it anymore. You'll just say, well, I could just draw a number line. Here's k plus 1, k plus 2, k plus 3, k plus 4, k plus 5, k plus 6, k plus 7. There's k plus 7. If this is remainder 2, then here's the cycle. Remainder 0, remainder 1, remainder 2, remainder 0, remainder 1, remainder 2, remainder 0. So I've got remainder 2 times remainder 0, but remainder 0 just means it's a multiple of 3. K plus 7 is a multiple of 3, therefore n is a multiple of 3 because it's a product of some multiple of 3. But I feel like once you've done this kind of number line analysis a few times, you wouldn't even need to do it anymore. You just kind of think, well, I could do that if I wanted to, and then I would know the answer. I don't personally care whether the answer is yes or no. I don't care. I just want to know that I could find out if I wanted to. So knowing about all this kind of number line remainder analysis, eventually you wouldn't even have to put pen to paper. You would just say, hey, good, this gives me that information I was looking for about divisibility by 3. Therefore, it's sufficient on its own. And the correct answer is B. So I wonder, did anyone use my notation for this question? Where that multiple of and remainder? So x is, in the world of divisibility by 4, remainder 3. Did anybody else have that? What about that next part? Up to the period. Nice. In the world of divisibility by 5, the remainder is 3. Now, at that point, did it strike anyone that this is an interesting coincidence? That you get the exact same remainder in 2 different worlds of divisibility? You got to ask yourself, is this coincidence really a coincidence? Or is it by design? Did the GMAT design it that way on purpose? I mean, what's the overlap between the worlds of divisibility by 4 and divisibility by 5?
Divisibility by 20.
That's right. The only kind of number that's divisible by both 4 and 5 is a multiple of 20. So if you have a remainder of 3 in both of those worlds, you must also have a remainder of 3 in the world of divisibility by 20. But how many different such numbers are there between 10 and 40? We know x is more than 10 and fewer than 40. So in the world of divisibility by 20, having a remainder of 3 would put you where? The number of members in this club has to be either 3, 23, 43, 63, 83, 103, and so on. But of all of those, there's only one number between 10 and 40. So now that we know that there are 23 members, let's keep reading. If they sit, who's they? The 23 members. If the 23 members sit at tables with 6 members at each table, so 6, 12, 18, except one and fewer than 6 members at that one table, so we're at 18, there's 5 remaining. Okay, so it's 5. Did anybody infer that there are 23 members at that point before continuing to read the question? That's the habit you want to get into to go to the next level. So the next level in the GMAT is to force yourself to pause mid-question, especially with these long word problems, right? You pause, you make the inference, and then you keep reading. Once I know the number of members in the club, now I'm ready to finish reading the question. And then when I get to the question mark, I already have the answer. So we've seen that happen before, but that's a habit that you want to develop. Imagine that I got a summer job as a counselor at summer camp. And I come home from my first day at work, and JD, who's my buddy, he asks, so how's your new job at summer camp? And I say, well, it's actually really cool because today I asked the kids to arrange themselves in groups of 4, and they did, and there was no kids left over. And then just for fun, I was like, okay, let's see if you can arrange yourselves in groups of 5. And guess what? they did. And there were no kids left over. It worked out perfectly with a 4 and with a 5. JD, what would you tell me at that point?
There are 20 kids.
You don't know for sure that there are exactly 20.
Could be 40.
You have to think in abstraction. You have to say there must be a multiple of 20. The number of kids must be a multiple of 20 because that's the only way that you'd be divisible by both 4 and 5. The least common multiple of 4 and 5 is 20. So if the number of kids in the summer camp is both a multiple of 4 and a multiple of 5, then it must be a multiple of the LCM of 4 and 5, also known as 20.
But I notice you only do this when the remainders are the same, but what if the remainder was different? Why can't you do it?
So let's imagine that I told you when I asked them to put themselves in groups of 4, there were 2 kids left over. But when I asked them to put themselves in groups of 5, it worked out. Then what can you say? You can say that the number of kids is 2 to the right of a multiple of 4, and also that it's a multiple of 5.
Yes.
So where could you find on the number line a number that matches that description? It's a multiple of 5, but also it's 2 to the right of a multiple of 4. That would be, for example, 10.
8.
10 fits that description, right?
Yes.
And where is the next number in the number line that would also fit that description? It would happen every LCM, every 20. So if 10 fits that description, you better believe that 30 and 50 and 70 and 90 and 110, all of those would fit that description. They'd all be 2 to the right of a multiple of 4, and also they'd be a multiple of 5. Okay. This is a tough question. We can say from the first sentence that in the world of divisibility by 5, n has a remainder of 1. And from the second sentence, we get another description, this time in the world of divisibility by 7, and the remainder is 3. So unlike the previous question, here there's no coincidence. We have distinct worlds of divisibility, but the remainder is not the same in both. And yet, there's still a coincidence. I wonder if anyone can see it.
It's -4.
Yeah, in both cases, we're exactly 4 units to the left of a multiple. I mean, if you have a remainder of 1 in the world of divisibility by 5, that means you're 4 below a multiple of 5. And if you have a remainder of 3 in the world of divisibility by 7, that means you're 4 below a multiple of 7. What a coincidence! There's no such thing as coincidence on the GMAT. They designed it that way. If you're 4 below a multiple of 5 and you're also 4 below a multiple of 7, then you must be 4 below a multiple of the LCM of 5 and 7. So that's the inference that we should make at that second period. N is 4 below a multiple of 35. Now I'm ready to keep reading the question. What is the smallest positive integer k such that if you add it to n, you get to a multiple of 35? Well, if I'm 4 below a multiple of 35, then that's how much I need to add to get to a multiple of 35. And the answer is B. Yeah, I think this question was designed to give extra time to people who see that and punish people who don't. Because with writing down the first 10 possibilities for n with the first sentence and the first 10 possibilities for n with the second sentence, you can find the overlap. That's what you did, JD. And that's what a lot of even GMAT teachers would do. They would just jot down, the first several possibilities, find the overlap. The overlap is 31. So they'd say, okay, n could be 31, and that's 4 below a multiple of 35, and that's how they would solve it. And that's fine. But as you said, you can speed up and then have extra time for other questions if you really understand divisibility and remainders at that deeper level. Yeah, I mean, so even without the coincidence, you know that the description that you got will recur every so often on the number line or whatever that LCM is. So that can be useful. And if all else fails, then you can just jot down the possibilities. And the way to do that quickly is to start with the remainder itself So that would be 1 in this case. And then start adding the divisor over and over again. So I'm adding 5 each time, and so on. And then here I'm going to start with the remainder itself, which is 3, right? N could be 3 based on that description. And then keep adding the divisor over and over again, like that. So that can be pretty quick, and then you just find the overlap. So that's like the low-tech way to solve the question. Imagine I tell you that I wash my car every 5 days, and I vacuum it every 7 days. And then I tell you that I washed it yesterday, and I vacuumed it 3 days ago. And my question is, when is the next time that my car will get that special day where it gets both washed and vacuumed in the same day? So that's analogous to the question that we just did. Right? I wash it every 5 days, and I washed it yesterday. I vacuum it every 7 days, and I vacuumed it 3 days ago. When's the next time that I'll wash and vacuum on the same day? If you know I washed it yesterday, and you know I wash it every 5 days, when's the next time that I'll wash it? 4 days from now. And then with the vacuuming, what did we say? I vacuum it every 7 days, and I vacuumed it 3 days ago.
Right, so 4 days from now.
And you're like, oh, what a coincidence. I'm washing and vacuuming 4 days from now, and the question wanted to know how long from now will I wash and vacuum on the same day? Well, there it is, 4 days.
I think what he's asking is the, like, why is the answer not 31 versus, like, 4?
Yeah.
Oh, because the question was, how many days from today will I vacuum and wash on the same day? The question wasn't asking, how many days ago did I wash and vacuum on the same day? It's asking, how many days from now will I wash and vacuum on the same day? If it was asking, how many days ago did I wash and vacuum on the same day, then the answer would be 31. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.